good morning. So, this work concerns the selection of a material for the production of a new laser range satellite that is going to be launched in less than 2 years, and this is called LARES-2. So, what is the importance of that satellite? So LARES-2 is a passive laser range satellite designed and developed for testing Einstein theory, and the use of this satellite will provide the most accurate measurement of intriguing phenomenon predicted by general relativity, with applications such as the generation of gravitational waves. So we obviously are looking at material for the construction of that satellite, and the basic requirement in designing this satellite is the minimization of its cross-section to mass ratio to reduce its orbital perturbation due to non-gravitational forces. The design on LARES-2 includes the choice of the base material that will be done on the basis of its density, while the specific alloy is going to be selected to meet other requirements. So, as you can see, the choice is not really a really easy task, because we have made several requirements. We have physical requirements, so we need a density of about 9 kilos per cubic decimeter, low sensitivity to heating by irradiation, because the temperature of the satellite must be kept quite low. It must have no magnetic properties and high thermal conductivity. We need to keep in mind that we need to produce a sphere, so we have also technological requirements such as good castability, because we need to produce a sphere having a diameter of about 40 centimeters, and good workability, because we need to produce cavities on the surface of this sphere. We have also mechanical requirements, so we need a hardness higher than 28 Rockwell C and a yield strength of about 500 megapascal. So in that picture you can see the image of the LARES satellite, so the LARES-1 satellite already launched. I'm showing you that picture because the geometry of the satellite is very similar to that one, but the LARES-1 was made of tungsten. So, to explain you the problem, so the mechanical requirement was imposed to withstand the high pressure at the contact surfaces between the hemispherical heads of the separation system and the hemispherical cavities located on the satellite. The pressure at the contact surfaces is a function of the Young modulus of the material selected. So if we select an alloy having a Young modulus lower than the one of tungsten, also requirement concerning the yield stress will be relaxed. So, as far as the material selection is concerned, after many studies, we selected some nickel and copper-based alloys that have been developed and studied. So, the first candidates were nickel alloys that have higher mechanical properties, but on the other hand, they are more expensive, and they have a low thermal conductivity. Why we need a high thermal conductivity? Because we need to reduce perturbations on LARS2. Among copper alloys, we had to select one having acceptable values of yield, strength, and hardness. So the first candidate we selected were copper beryllium alloys, but the toxicity of beryllium would have introduced additional concern that would have delayed the LARS2 program. So among copper alloys, we selected two particular alloys, the C70-250 and the C19-500, that were produced in the lab and were tested to know their properties. Unfortunately, the C19-500 alloy was magnetic, and after heat treatment, its hardness did not reach the minimum value, which was 28 Rockwell C. The other alloy fulfilled all the requirements, but this alloy is commercially used as a broad alloy and for producing very small items. So we need to keep in mind that we need to produce a sphere that has about 40 centimeters of diameter and a mass of about 350 kilograms. So we need to know the properties of the alloy in the S-cast conditions. So aim of this work was assessing possible critical issues concerning the toughness of the alloys subjected to different heat treatments. Talking about the satellite, in the satellite body, the maximum hardness is needed in the areas in which the satellite is in contact with the separation system, but in those areas, a low fracture toughness will not be a problem, a concern. Greater fracture toughness is required, on the other hand, for producing the screws used to fix the mounting system of the cube corner reflectors on the satellite. So we produced, the alloy, the selected alloy was produced in a vacuum induction furnace and producing big ingots, so in the range 5 to 12 kilograms. In the table, you can see the nominal composition of the alloy and the real composition of the alloy we produced. So as you can see, only say nickel content is slightly higher than the nominal composition range. After that, we performed solution treatment at 900 degrees centigrade and water quenching, and then we performed aging. So as you can see from the diagram, hardness reaches maximum values between 8 and 14 hours, and then it decreases due to overaging. After that, we tested mechanical properties of the selected alloy. So, as you can see, after aging for 14 hours, we had a yield strength of 540 megapascal and hardness, Rockwell hardness of about 30. But unfortunately, we had an elongation of about only 2%. So selecting this material could be a concern for the production of the screws. So we thought that the best solution could be to produce this body of the satellite by using this alloy, and to produce the screws by using the alloy in the overaged conditions. So for example, you can see that after 24 hours we have a yield strength which is still quite high, so it is high enough to guarantee good tightening of the screw. And the elongation increase reaching about 4 or 5%. So more information could be obtained by looking at the fracture surfaces of the tensile specimens. So as you can see on the left, we have the fracture surface morphology of the alloy after solution treatment at 900 degrees centigrade. So you can see the surface is characterized by dimples. On the right, you can see the fracture surface after aging performed for 14 hours. So in that case, we see that we have a mixed mode mechanism. So you can see areas characterized by dimples, and so here dimples, and areas characterized by brittle interdendritic fracture. Again, looking at the fracture surface of the specimens after aging for 24 hours, we see again a mixed fracture mode. So again, we have in some places ductile behavior and brittle behavior in other areas. And here you can see a different magnification, the fracture surfaces of the V-notched specimen used for Charpy tests. We performed those tests on specimen treated for 24 hours, so in the overage condition, obtaining an impact energy of about 90 joule. And on the fracture surface, you can see that we have areas, small areas characterized by brittle fracture, very close to areas characterized by a ductile fracture. Another important test is to evaluate the machinability of the alloy. So you can see on the left a detail of a screw. So we produced the screw using the overaged alloy, and as you can see, the surface of the pin is even, and you cannot see cracks or irregularities on the surface. On the right, you can see a SEM micrograph showing the box. So that's, say, the female thread. In this case, we obtained that on the alloy aged for 14 hours. Even in this case, you can see that there are no cracks or irregularity on the surface. So, as a conclusion, the data obtained with this study suggested that the most interesting candidate for the satellite is the C70-250 copper alloy in the age-hardened condition, because it meets all the design requirements. Screws that need to be characterized by a higher toughness and workability could be produced by using the alloy aged at 500 degrees centigrade for 16 to 24 hours. Thank you.